Good afternoon. Thanks for coming today to today's CyLab seminar. Our speaker today is Ken Mai, who is a senior systems scientist at Carnegie Mellon University. Ken's primary research interest is the circuit design of efficient, high-performance digital blocks, that is, memories and functional units, in future generation technologies. The title of his talk is Building Secure, Reliable Hardware Roots of Trust. Are PUFs enough? Thank you, Ken, for presenting today.
All right, thanks. So today's talk is really sort of half of a position paper and half of a technical talk. And personally, I think the technical part is a little more boring than the position part. So what I'm going to talk about is start a little bit with hardware roots of trust. We'll go over just a little bit of sort of general background, and then talk about physical clonable functions, some of the results that we have from previous test chips and other people have about what their features are, and then really try to match that up against what you need in a hardware root of trust. So first is my sort of very generic trend intersection slide showing the need for secure systems. Right? So first is there's globalization and diversification of both the design of ICs and manufacture of the ICs. You have more and more of these ICs in portable Internet of Things and medical applications. For those of you who don't know, on the bottom row on the left is a tug robot. So anybody that's spent any significant time in UPMC lately has probably seen a tug robot. It's actually built in Pittsburgh. It's a little automated thing that drives around and delivers medicines and things like that to the nursing station, and actually is quite a lot of consternation to the doctors because it gets in their way and stuff like that. It can call the elevator, it can do a lot of cool stuff. On the right over there is portable X-ray machine, made by GE, I believe, but it basically takes, they can wheel it over to wherever they want to in the emergency department or wherever, take the X-ray, and it sends it over to radiology for the reading, and then obviously a nest and then some other things. All right. Obviously, we're keeping more and more sensitive data in digital form, so the new passport, credit card information, and then proprietary, military or industrial data. And finally, the hacking methods are getting better. We're going to go into a little bit more detail about the hacking methods, but over here on the bottom, you see focused ion beam alteration of a chip. You see some direct probing of a chip, and then finally on the right, there is a setup for a side channel attack to measure the power dissipation in a chip, and then use that as information to crack the encryption. Now, again, so overall, the trend intersection is driving towards secure systems. And the sort of fun example I like to use is this one over here from the last World Cup. So that's a picture of Neymar getting kneed in the back. And for those of you who remember or follow it carefully, he damaged some of his vertebrae. But within like a day of this happening, right, all over the internet was the X-ray and the MRI of him doing it, right? So there's data that's running around in these systems that you probably do want to protect. Okay. So let's talk a little bit about hardware roots of trust. So this is just an example hardware root of trust showing that you have your sort of overall system here, and at the core you have this little piece of it that you're going to use to build out trust for the rest of the system. Right? And what does it do? Well, there are various functions. It can store or generate your keys, which is mainly what we're going to talk about today. It can securely store data, and then has your crypto primitives inside. Right? And what you want from it is you want tamper resistance, you want resistance to attacks, and we're going to talk about a more specific example in just a second. All right, here's another example of hardware root of trust, probably more familiar to you is the TPM, or Trusted Platform Module. Right? So there's a specification for a crypto processor. It's deployed in a ton of PCs and mobile systems, and the specification is evolving in multiple iterations. Now, the one that I want to talk about specifically today is a very cut-down version of this. So this is the hardware root of trust from a DARPA program that came out about a year or so ago called DARPA Shield. Right? And the idea here is what they wanted to do is they wanted to be able to track ICs through the manufacturing chain and through the deployment chain to mainly combat IC counterfeiting. Right? So this is a big problem for DoD-type agencies where they have chips that are going into deployed systems, and they found a number of them that were counterfeit, even though they're in the avionics package of a helicopter and things like that. Right? So this is a very scary problem. So the idea behind DARPA Shield is that they're going to build this tiny little chiplet, right, 100 microns on a side, and they're going to insert it into the packaging of every IC that was manufactured or used in military systems. Right? The reason they don't want to force people to include that on the actual chip that goes into the system is because you can't go to 20 different manufacturers and say, hey, by the way, can I stick this mysterious piece of silicon or design piece on your die? Don't talk to me about it. I don't want to tell you anything about it, but I'm going to stick it onto your die. So the idea, again, was to stick this tiny piece of silicon inside the package itself and then go through the deployed chips. Now, the use scenario is that some private or whatever was going to go through, grab this board that was going to go into an airplane, and then take this probe and jam it over every chip to verify that it was a genuine chip, manufactured in the right time frame, and so on and so on. All right. Now, the hardware trust is a little bit simpler because they rely on the fact that they have this secure back-end database and everything else. So how does this guy work? So when the probe gets on the chip itself sends back a serial number, right? And that serial number gets fed through the database and matched up against a challenge response database for the PUF or whatever challenge response system you have. That challenge gets sent into the chip, and then the chip sends back the correct response for that, right? And if those two match up in the database, then you're happy. If they don't match up, then you have a problem. Now, in addition, the chip was supposed to record a number of other things about its environmental condition, tamper state and everything else, and send that back as well. But the point we're worried about is just really this piece here, where the chip sends back an identifier, the system matches that against a challenge response database, and then does this challenge response to verify that the chip is a genuine part. Now, just the threats that we're worried about here are mainly threats to the supply chain, right? So over here is a little diagram showing where your electronics get made, right? So going from the tool design to the design itself, to the manufacturer, packaging, everything else, and clearly it goes sort of all over the world to get made, and this is concerning because you never know where along that supply chain someone might try to compromise your design. All right? And similarly for software as well, you may or may not have good feeling for where the origins of that are. Right on top of that, the tools themselves that you're using to build the chips are third party. Those can get compromised, and same with the software. All right, so the counterfeiting threat, I mean, for those of you who aren't that familiar with it, I'm sure some of you know a lot about it, but it varies from very high tech to very low tech. Right? On the low tech end, you have a container ship full of electronics getting dumped onto the shore. Guys paw through it. They literally wash off the electronics in the river, hold it over a fire, pop the chips off, remark them or maybe don't remark them, and sell them back into the supply chain. Now, one thing you might be wondering is, well, how does one of these chips that has that happen to it, right, end up in some Boeing airplane? Right? What tends to happen is Boeing goes and they request a certain number of parts of a specific IC from their main supplier, right? And if their main supplier has them all in stock in a warehouse someplace, great, they send them on. Sometimes their supplier has 14,000 of them, where Boeing asks for 15,000, and then their supplier then goes deeper in the supply chain and asks somebody else for them, and so on and so on. Right? And at some point, it ends up at one of these companies. Sometimes, again, very low tech like this. Sometimes, a very above board 10,000 person company, supported by the government to, not our government, but other governments to supply the chips in. Now, the problems can be both recycling, right? They just pop the chip off, sell it back in the supply chain. The danger, of course, is obviously it's been used before. It's gone through, who knows what kind of heating cycles and so on. So it could be pretty unreliable. Remarking. So one of the things that drives the profit motives for these guys is they'll pop off a chip, and then they'll say, oh, you know what? I think it really is, can run a little bit faster than that. So they scrub off the markings and mark it with a higher performance one. Or scrub off the markings, and whereas it was consumer spec part, they'll mark it mil spec, and so on. Right? Then unauthorized production, this is what, I like the name of this, is sometimes called midnight fab. So this is where, right, a lot of the manufacturing for ICs is overseas nowadays. So you send your design overseas to get manufactured, and you order 10,000 parts. Well, you get your 10,000 parts and you're happy. But it turns out that in third shift, they suddenly manufacture 5,000 more parts that you didn't order, and then they sell those as counterfeits. All right? Then outright cloning of the designs. Right? When I send my design over to get manufactured, I just send a big pile of electronic design database, and they can take that, they can copy it, and do things to it. And then finally, sort of the nightmare scenario as far as DoD is concerned is that they copy the database, they alter the database, and then manufacture as well. Right? Now, the impact here from an economic standpoint is relatively large. Counterfeit electronics overall is about a $100 billion a year industry. For ICs themselves, about a tenth of that, about $10 billion or so. And as I mentioned before, there have been counterfeit ICs found in deployed military systems before. There was a Defense Science Board report not too long ago that disclosed 3 different instances, but as you can guess, there are a lot more. So down over here on the left is a relatively famous incident, I think from 2008, where there were entire Cisco routers that were counterfeit. Right? And they were sold to the FBI and the Navy and a number of other places, and they were caught relatively late And I'm not remember sure if they were actually powered on yet or not. But just looking at the differences between them, and they look pretty good. OK, so what do I need in my hardware root of trust? Right? So for this very simple one, I just need a couple of components. I need something to either generate or store my key, and then a crypto engine. All right? My necessary features, right? I'd like it to be hard to reverse engineer, resistant to a number of different forms of attack, resistance to sort of invasive tampering. Now, this is interesting. So tamper-resistant and fragile, and this is going to come up a little bit. So if you look at the recent calls from DARPA and a few other places, one of the things they almost always ask for nowadays is that it be tamper-resistant and that the key or whatever secure data you want gets erased on tamper. Okay? It needs to be reliable. This becomes a problem for PUFs later. And then compact, low cost, good performance, everything else. All right, so primarily today we're going to talk about the key storage in relation to PUFs. Now, so this is sort of the overall kicker slide. And so on the two rows are PUFs, right, physical and global functions. We will talk about them more in a bit. And then just non-volatile memory, just storing your key. All right, so pros and cons. Right, on the pro side for PUFs, the good thing about them and the thing that people usually tout about PUFs is they're hard to reverse engineer. Right, that the data, the key stored is in some little variation in the devices on the die, and it's hard to tease out. Right, so it's hard to reverse engineer. Right, it's an inherently generated key. You don't have to do anything to it. The key gets generated from the process manufacturing and the circuits, and usually there are no special processing steps. That applies mainly to silicon PUFs. People have done like optical coding PUFs and things like that require special steps, but we're just talking about silicon PUFs here. Now, on the con side, one of the big ones is that it's not erasable, right? So I talked about fragility a minute ago, but because the key is generated from these process variations, that's inherent in a manufactured die, right? It chunks out of the factory, it has certain variations in the processing, and that's what you get as the key. And it's very difficult to erase that. You can't, from normal silicon processes, erase that, right? Next is it's not testable, right? I can bring it up, I can power it, but in order to know whether it's not reliable or not, I have to hit it 1,000 times, 10,000 times to know whether or not it's going to be reliable. But sort of inherently, it's not testable. I have a reliability problem. We'll talk about that from silicon data in a minute. And usually, the designs have relatively high overheads, right? Compared to just storing the key in some non-volatile memory, the thing's usually pretty big, pretty power hungry, and so on. Now, on the non-volatile memory side, the good things are, well, it's erasable, testable, reliable, and low overhead, right? So pretty much, you can just swap those two segments. Now, on the cons, it's relatively easy to reverse engineer, and there's some variability in how true that is, right? It was only in the past couple years that people could go through with a probe and actually read a flash cell, read the VT level of the floating gate. But if you talk to the guys from Chipworks and stuff like that, they've reverse engineered flash for a number of years simply by digging down and getting access to the IOs of the memory itself and just reading it out, right? So they just probe the address, they probe the data lines, and can read it out. But if you want to directly probe a cell, that's actually pretty hard, all right? It does require a secure access path, right? At some point, I have to write in the key, so I need some way to write it in, and then some way to close that path off. And then usually for non-volatile memory, I need some special processing, right? Building a flash memory cell is really different from building an inverter, right? So there are special process steps which increase cost and complexity and that sort of thing. All right? So what are the problems here? So the problem is that the PUFs can't meet the fragility and efficiency needs, right? They're not reliable enough. They have relatively high overheads. And on top of that, they can't meet a basic feature, right? That you can't erase them. All right? Now, the non-volatile memories, the downside is that, well, they're more vulnerable. It's a little questionable, but they're more vulnerable. And they're more expensive because they require more processing steps. Right? So the problem here is that really neither non-volatile memories nor PUFs really meet all the needs that I want from my hardware root of trust. All right, so let's talk a little bit about key storage and non-volatile memory. Right, so what are my choices? Right, so I can do a ROM, right, a read-only memory. Not very interesting because I can't rewrite it. Right, I can use eFuses or some kind of non-volatile memory, whether that's an EEPROM or a flash or an emerging non-volatile memory cell. Right, so over here is an eFuse. Right, that's the fuse itself, and then that's the fuse getting blown over there. Right, and then a floating gate device over here. So sort of an older generation flash device. So what are the problems? Well, I have some data remanence issues, meaning after I've written the data in there, erasing it can sometimes be a problem. I can do side channel attacks on them. In the latest generation non-volatile memories, I have this real big problem called cell-to-cell interference. So this is related to some of the work that Oner's done recently on DRAM and that we've done on flash before, which is when you write one particular cell, it actually affects the neighbor cells because they're just so close together. Right? So I can use that as a side channel attack, either to maliciously try to read a cell or maliciously try to write a cell by having a cell affect its neighbors. And then finally, direct probing, which at least in some cases has been effective. All right, for data remanence, right, the issue is, right, the data stored in the cells permanently alters the cell in some way. Right? In Flash, for example, one of the things that happens is that you need to fully erase the cell to get rid of all the electrons sitting on the floating gate. Sometimes that doesn't happen perfectly. You can read out some of the old data based on that. Over here is a very ineffective technique for erasing Flash. So this is a company in the UK that promises to destroy your SSD. And all they really do is they come in and, hopefully you can see it, they just crack the chips, right? And for anybody knowledgeable a little bit about ICs, right, that just because you destroy the package doesn't mean you destroy the chip. And if you care enough about it, you could probably depackage the chip, repackage it, or probe it, and then get the data off. All right, side channel attacks. So the issue with side channel attacks is that, right, the systems themselves often send out information on channels that are not the primary IOs, right? So it could be sound, it could be EM waves. The most common one to use nowadays is power, light, or some of the other outputs, right? So delay in the output, delay in a different output, and so on, right? And this has been used successfully to crack encryption systems. Again, primarily the setup over there on the right is looking at the power supply distribution. Cell-to-cell interference, right? So this is an example in flash memories that we looked at before. So first, this is the SEM of the flash memory cells. And what you can see is that they're packed in really tight, right? It makes sense because as a memory manufacturer, designer, what you're trying to do is you're trying to sell as many bits as you can in as small a piece of silicon as possible. But the problem is that, again, by writing one cell, you can affect the other ones. And you can use that technique to both maliciously write data or read data out. And finally, direct probing. There are a number of different ways to do it. This is a decapsulated chip over here. This is a probing station. And this is from a paper a number of years ago using light emission on the chips to probe out the values as well. Right, so there are a number of different ways you can do that. All right, so let's look at the other key option, the other key storage option, which is PUFs. Right, so it's a physical unclonable function. There are a lot of different types. We're going to talk mainly about silicon PUFs just because they require kind of the least overhead, the most integratable. Again, there are optical PUFs and a few other things, but the silicon PUFs seem to at least have the best chance of being integrated onto usual dies. Right? Again, the vulnerabilities are you're not going to be able to erase them. They're hard to test, and they have relatively low reliability. Or that reliability can get traded off against high overheads. Right? You can use a lot of ECC and stuff like that to boost the reliability, but it's very expensive. All right, so just in general for PUFs, right, the designs themselves are very different from typical digital design. Right? In typical digital design, your goal is to make sure that no matter what happens in the process variation, right, your output isn't going to depend on the variation. Right? Whereas for a PUF, you want the output to very strongly depend on the variation. So it's sort of a flip side of the common digital design philosophy. Now, as far as sources of variability, the primary one that people have been taking advantage of is random dopant fluctuation. So the issue here is you're implanting atoms into the channel of the transistor, and they distribute in that channel somewhat randomly. And so the VTs, the threshold voltage of the transistors, varies by quite a bit. There are a few other phenomena that you need to worry about, but random dopant fluctuation is really dominant in modern technologies. So as far as the concept goes, right, you have this distribution of threshold voltages, or maybe comparisons of threshold voltages or delays or something in the design, and you split that distribution, calling one side 1, one side 0. Right? Now the issue is that with variability, the distribution can move back and forth, and so I can have some issues with how evenly distributed those 1s and 0s are. Right? The shorter, the fatter my distribution is, the better, because then I have more of the guys in the tail on either side. So as far as design goals go, what do I want for the PUFs? I want them first to be random, right? So they can't be modeled. There are a number of PUFs like the original Arbiter PUF that are really bad at this. Like they actually are pretty easily modeled. But that for some number of challenges that go through the system, the responses are going to be random. I want them to be unique per die, right? So if I take the same challenge and put it through 3 instances of the PUF, I get 3 different responses, 3 very different responses. And finally, I want them to be reliable, right? So across different environmental conditions and IC aging, that the response is consistent across all of those different phenomena. as far as implementation goes, there are delay-based PUFs and bistable-based PUFs. Right? The delay-based PUF are mainly the arbiter and the ring oscillator ones. If you squint hard enough and sort of pull back, they actually are the same. And then there's a bistable element PUF, so you have some element that locks one way or the other, and use each of those to generate a bit. And again, if you pull back even further, then these basically are sort of degenerate versions of ring oscillator PUF, sort of a one-element sort of ring oscillator PUF. Arbiter PUF here is I have these two delay paths I can go through. These are muxes, so I can choose whether I go top or bottom. The challenge comes across here and sets those muxes, and these two paths come through at the end to an arbiter, and the response bit depends on which one comes out first. All right, so I can choose with a certain challenge, to set the paths, the blue versus the red, and then it depends on which one comes out first for the data bit. Ring oscillator PUF is very similar. It uses a set of ring oscillators, so each of these guys is a ring oscillator, and you compare the oscillation frequencies. Right? In some ways, you can think of this as taking those two delay paths, allowing the difference to accumulate for a number of cycles, and then checking the result. So it's essentially the same thing as an arbiter PUF with an ability to increase the reliability by just waiting longer through the system. All right. So the bistable PUFs typically rely on having a cross-coupled inverter pair that locks either 0-1 or 1-0 in the state, and then you just power the thing up, and it goes one way or the other depending on the process variations of the devices in there, and then that's your bit that comes out. So one thing we were interested in a number of years ago is we were interested in just comparing the different kinds. Right? People had discussed a lot of the different types, had built some prototypes, but not all together with the same effort and so on. So we just built this chip a few years ago to check to see what the differences was between them. And then what we found, and I'll just go through this quickly, is that the randomness in general was OK. We did this, which is a very coarse 1-0 test. We did NIST and everything else, and the randomness was generally OK. Similarly, the uniqueness was generally OK. We probably could have taken a few more data points for that guy over there, but they all distributed relatively well across the different chips. There wasn't a problem there. For reliability, we took the test boards, we shoved them in a temperature-controlled chamber over there, ran -20 to 85, and ran plus and minus about 20% on the VDDs just to look at what the reliability was. And the somewhat surprising thing, it shouldn't have been that surprising given the literature, was the reliability was terrible. Right? So along the bottom here are the different PUF types, arbiter, ring oscillator, and a couple of bistables. And on the y-axis here is the percent errors. Now the percent error here isn't for a particular data point, but it's the number of bits or the percent of bits that flipped at some point in the sort of cluster of voltage and temperature. Right? And even for the kind of best types over here, the maroon bar here is for voltage and temperature, the green is for temperature only variation, and the blue is for voltage only. And what we saw is that it was pretty bad. Right? You're not going to be able to tolerate 13% error in your encryption key. Right? If you wanted to do like some weak authentication or something like that, maybe that's OK. But again, for encryption keys, this was clearly way too bad, right? Which is why people moved towards ECC. Now, one of the other things we're interested in looking at is, we're VLSI guys, so we're just interested in what the core metrics were. So as far as delay goes, the bistables are much better, right? You power them on, essentially one cycle, nanosecond or less, the thing gives you your bit out, right? The arbiter, you have to wait for all that delay to go through to finish. And the ring oscillators, you just sit there and accumulate the difference over and over again, so it takes even longer. For energy, similar sort of story, right? It takes a lot of effort and circuitry to go through the delay guys. The bistables are much lower in energy. And finally, for the area generated bit, the bistables are much smaller than tons and tons of gates. Now, this is a little bit unfair because for the arbiter and ring oscillator, you can, in theory, reuse some of the elements and do it over and over again. The downside is in reusing those elements, you obviously have a reduced pool of entropy, and so your modeling, your vulnerability to modeling a task goes up by quite a bit. So the upshot is that, right, for the different kinds of PUFs and the different features, right, they're all pretty random, they're all pretty unique, that's pretty good, and all of them have great reliability, right? For VLSI features in general, the bistables are better, and so what we were thinking is, well, can I trade that for that, right? Can I go through and say, look, if I take the really good VLSI features, and I'm going to just tune them down a little bit, I'll burn a little more area or burn a little more time, can I get my reliability back, right? So this led to sort of a whole line of research in how to do that. Now, the typical way that people get reliability is using error correcting codes. And these are pretty heavyweight error correcting codes. If you think about, I have a 256-bit key. I lose 10% of that. That's 25 bits. Right? Already ECC for to get 1 bit back is really hard, or kind of hard. But 2 bits is really hard. 25 bits is a real pain. Right? So they're relatively heavyweight ECC algorithms. They require pretty significant overheads. And you need usually a ton of helper data, thousands and thousands of bits, and then a lot of delay. They generate a key in 12 microseconds, right? Which, from an electronic standpoint, is forever, right? So, from the standpoint of PUFs, right? Again, there are a lot of PUF types. There are a lot of vulnerabilities, and we've seen this issue with reliability. Okay, so let's talk a little bit about the erasability, right? So the PUF response is an inherent part of the design itself, right? The physical structure. But it's not part of the database, right? That's the whole point of it. But again, the problem is that because it's an inherent part of the physical design, I can't erase it, right? So I don't have this feature in non-volatile memory that I need. Now, this is a paper from a number of years ago, I think from TU Berlin, right? Which was called Cloning Physical Unclonable Functions. And this led to this response from a lot of places, right? Because people are like, oh my gosh, this PUF thing that we thought was going to be great and save everybody is going to be the end of the world. Now, the issues with the paper are, and I know the guys who wrote it, I like them a lot. The issue with the paper is that they used some pretty well-known techniques. The technology was pretty old. So there was some question about whether or not if you built a sort of bleeding-edge design, whether they could really do it. But then I thought about it a little bit more, and the real problem, or the real thing that's concerning about this paper is not about the technology and whether or not you can read the data out and all this sort of stuff, right? Or, for a particular design. The problem is that it highlights the fact that the PUF response, right, the core secret you're trying to store or keep secret, right, is physically manifested in the design itself, and you can't get rid of it, right? So this really highlights the non-erasability of the PUFs. Irrelevant of how the technology they use and all this sort of stuff about being able to read it out, the point is that it's there, and it's always there, and you can't get rid of it, and that's really the problem. Okay, so this next part about testability, right? So, from the security standpoint, right? You don't want this ability to pull the PUF values out of the chip and be able to read them sort of in a normal digital way, right? Because that's a problem. It allows the attacker to use that as a vulnerability. There have been a number of examples of people attacking the tap or test access port. So they attack the normal scan path that manufacturers use to test special features and stuff like that, and they can open it up. So it's a vulnerability, right? So I could do e-fuses, but I could fib close the e-fuse and do it again. And so the problem this leads to is that the test time for PUFs is really, really long, right? Because if I can't just suck the secret out quickly, suck the core of the secret out, the only way I'm going to test it is by just hammering it with challenges. Now, for those of you that know a little bit about IC test, right? A typical IC, like a little cheap one, spends order seconds on the tester, right? A really expensive like microprocessor spends a few minutes on the tester, but that's it, right? So if you go to these guys and say, oh, okay, by the way, I need you guys to test the PUF by running at multiple voltages, multiple temperatures, which takes a while to stabilize, and then pull out 10,000 charge response pairs. You're not even going to get past an initial design phase. They're never going to do it, right? So you have this problem where you need to do all this testing to make sure it's okay, but you can't possibly fit that into the testing cycle for an IC. One of the other things, I guess I should have added another Sky's Falling thing. So there was another paper by, I believe, Christoph Parr that showed this kind of attack on an Arbiter PUF. And what they did is they went through and on the design database, they basically drew low VT devices all on one side of the Arbiter. Right? So it basically makes one side of the Arbiter much faster than the other side of the Arbiter. All right? And this, again, caused a lot of consternation in the DoD circles because this was sort of this manufacturing-based attack on the PUFs. And if you don't do this, right, if you don't test it, you're never going to catch this. Right? Some malicious guy in your fab changes your mask set, and then suddenly your PUFs are all skewed one way. But because you don't test it because you can't afford the time, then you'll never know that that's going to happen. All right, so let's talk last about reliability. So this is the plot I showed a minute ago. And so for reliability, right, it's hard to achieve. Your two choice paths are either to go for error correction, or in our case, what we looked at is error reduction. Right, now the reason we looked at error reduction is because, honestly, I'm not going to say stupid, but I'm not an algorithms guy, right? I'm a design guy. So I'm not going to go through and go through the dozens of papers on ECC and the 30 years of theory on ECC to figure it out because I'm just not that smart, right? So what I know how to do is I know how to hack circuits. So when we looked at error reduction, we had two different kinds of techniques, what we called extrinsic and intrinsic techniques. The extrinsic techniques were things that wrapped around the PUF to build up the reliability and kind of simple stuff, right? Majority voting after multiple activation, that sort of thing. And then intrinsic techniques, which we think end up being more powerful, which is just looking at the core circuit and how to make it more reliable. All right, and what do we come up with? So the extrinsic stuff, right, I said, multiple evaluation, majority vote, activation control of some of the signals, and we could do okay, right? We could reduce that, 10, 20% errors by about 70%. We could bring it down, so it's a single-digit percentage error. But that wasn't, again, not good enough for encryption keys by itself, but maybe you reduce the ECC burden, there's less ECC, everybody's happier, okay, fine. Right? The intrinsic techniques we were looking at were post-silicon selection and response reinforcement. Post-silicon selection, right, again, pretty simple. You go through, you do a little bit of testing. We had a way to reduce the testing by quite a bit. You pick out the good ones, you store that, you use the good ones. And the one I want to talk about mainly is response reinforcement. So response reinforcement, what we do is we take this initial distribution we have of whatever electrical parameter we have, right, we're measuring, and it's split 0, 1, right, again, but the problem is that as this distribution moves around, I can have some unreliability. And first, we flatten it a little bit, right, make the tails a little bit bigger, and eventually what we want to do is do this, right, which is we want to pry the two distributions apart. So there's this dead zone in here where we have no bits, and even if these distributions vary around a little bit, it's not going to cross that boundary, right, so we don't have unreliable bits because of that. Now, the way we're going to do this is we're going to intentionally use IC aging effects, right? So in modern IC processes, there's this big concern about aging effects. So things like negative bias temperature instability and breakdown of dielectrics, electromigration, all this sort of stuff. And what happens is that as you use the chip more and more, the devices on it degrade in various ways, right? And so getting the lifetime of a chip to be 10 years continuous operation is actually a big challenge nowadays. But what we're going to do is we're going to pick one of these effects, some of these effects, and we're going to intentionally use them to hammer the transistors to split those two distributions apart. Now, originally we tried MBTI because it was easy to do, but the problem with MBTI is that it's pretty reversible. What the phenomena is you have a transistor channel where the current flows through here, and there are little traps on the interface of the two materials, of the oxide and the silicon. And you can trap carriers in there and change the VT of the device. Right, the problem is it's right on the interface. They're easy to pop on. They're easy to pop off. Not very good. What we end up using is hot carrier injection. In hot carrier injection, what happens is in the transistor oxide itself, there are defects. And if you have a big enough current running through the device, some of those high velocity carriers actually get embedded into those traps in the oxide, and they stick there. So again, another way to permanently alter the VT, or not permanently, but at least alter the VT of the device, hopefully permanently. The good things about it are that it's relatively easy to induce. I need only about 2.5, 3 volts. Now, for those of you who know something about chips and interfaces, usually you have a chip, the core might run at a volt, but the interface runs at 2.5 volts or 3 volts or whatever, right? So you already have that voltage on the chip anyway, so that's pretty easy. Short reinforcement time, so order 10 seconds to low hundreds of seconds reinforcement to change the VT. Now, even that is concerning, right? I mean, we were talking to, I think, Qualcomm once in one of these CyLab meetings, and like, well, like 10 seconds. And the test guys kind of look at each other like, oh my God, 10 seconds. Right? The good thing about our particular technique we'll see in a bit is that you can do it at any time when the chip is powered. You don't need the tester or anything else, so you can find that time. Strong reinforcement effect, you need to move the VT by about 50 millivolts or so, and then high permanence, and we've sort of artificially accelerated some chips for a long time, and they still kept this property. All right, so what is this effect, right? So I have this transistor over here, and what I'm going to do is I'm going to drive a big current through the channel of this device. Right? And as I drive that big current, there are going to be some high velocity carriers in here, and what they're going to do is they're going to pop out of the channel, and they're going to embed themselves into the oxide of the device. Right now, the funny thing is that they embed themselves in this region here. This is sort of the high field region of the channel, so they embed over here on this corner. Now, the problem with doing this is that if I continue to run current this way, those carriers don't have a big effect on the VT of the device because they're not over the inverted part of the channel. So really, when I use the device, I actually need to run it in the opposite direction. This isn't that critical, but it's just a thing. Okay, well, here's the design itself. In black here is the core of the design, which you'd have normally. And all the blue stuff is the support circuitry we added This was pulled together relatively quickly because we thought of this close to the tape-out deadline, but we've reduced the overhead by quite a bit. All right, so there's the design itself. There's the there's the test chip, whatever. We did about 1,600 of 2 different types of this thing on each test chip, and what we found was pretty good, right? So this is sort of the key results slide. So on the very top is the distribution of the VT differences at baseline without reinforcement. And then way down here is about 2 minutes of HDI stress, right? So we've done what we wanted to do, right? We pull the 2 distributions apart, and so now there's this big dead zone in the middle so that even if these guys move around due to voltage or temperature, they're not going to cross the center point. So reliability plot. So there are 9 plots here. So each of the plots is a different voltage and temperature corner, right? And this is how much we moved the VTs of the device, and this is the reliability over here, right? What we're shooting for encryption keys is a bit error rate around 10 to the minus 9. And so we've had this thing in the lab for a long time. And so you'll notice that these marks are somewhat different from those marks. So these final marks were where we shifted the VT by about 50 to 60 millivolts, and we never found an error. Right, so we ran this thing for, I think, 2 weeks continuous, and we still never found an error. And we kind of stopped when my student got bored, and then when we hit 10 to the minus 9 on the bit error rate. So basically what the ECC guys shoot for in terms of reliability of the designs. All right? So, again, the good thing is, right, with measured data, bit error rate around 10 to the minus 9, key error rate, 128-bit key, around 10 to the minus 6. And that's pretty much the target for the reliability guys, or for the ECC guys. All right? So just a recap of the design, again, good reliability. I didn't need helper data, so there's no other data to move around that I need to do the ECC. It's fast. I get the response in about a cycle. It's relatively simple to do, a relatively short reinforcement time, and high permanence. So what we did is we baked the chips at high voltage to simulate 2 years of aging, and these results here are for the chips post-bake. So they've already been baked, and then we get the result out. Okay. So back to kind of the original point of the talk, right? So with the response reinforcement, we did that, right? And I think we were pretty successful in doing that. You can see the distributions, everything else. Now, if I compare that, which is what we were trying to do, to some research that one of my other students was doing on flash memory, this is the distributions of the VTs of a single-level flash cell, both for 0 and 1, programmed in arrays, right? 0 and 1, right? And they basically look the same. So, at the end of the day, we did all this work, and what we really made is sort of a weird-looking, non-volatile memory, right? Because we did this, right? Split distribution, 1, 0, 1, 0. Now, our particular design, sort of writes its own data, right? It sort of figures out its own natural inclination, 1 or 0, and then reinforces that. But essentially, I've done the same thing, right? I could do that with a flash memory cell if I wanted to, but I've just basically built a sort of CMOS logic process compatible flash memory. Right? So that's sort of good. And if you think about what we physically did, it's nearly the same as a modern flash memory. So in an old-time flash memory here, what you had is a floating gate. You have this floating piece of polysilicon inside the oxide that you shoved electrons onto or pulled them off, right, to set the VT of the device. In a modern flash memory, that's too big of a structure. So they actually have an oxide, and they have this special little layer. It's not quite a conductive layer, but it's sort of a nitride trap layer in there that they shove electrons in and pull off, which is essentially what we did without building a special layer, right? So we're sort of a cruddy flash memory in some ways. But the physical structure that we built is essentially the same as what they do in very, very new flash memories. All right, so let's go back over here. So, right, the early slide that I showed you about, what is the talk about looking at PUFs and non-volatile memories, right? Having both pros and cons and not any of them being able to fit what we wanted to do. Right, but if we look at the PUF that we built, and in the end, it's not really a PUF. Right, we do actually get back some of the features you want from non-volatile memory. Right, you can be erasable, right? Because now I can write that cell this way, right? I can split the cell, but I can also, if I want to erase it, take the other side and just smash it the other way. So I can pull all of them to 0 or pull all of them to 1 if I want to. Right, it's just that the normal operating mode I don't. Right, so on tamper detect, I could actually erase the structure. Right, from a testability standpoint, I can read out the core of the memory, the core values of the PUF. So it's relatively easy for me to just scan those values out. There's some additional complexity about closing off the test path and things like that. Reliability we've already talked about. And for low overheads, again, the bistable PUFs are much smaller, much more compact than the delay-based or arbiter ring oscillator type ones. So we've got the reliability, or the overhead stuff as well, right? So in some ways, the kind of hybrid PUF NVM that we built pulls almost all of the pros out of here, with possibly the exception of testability that we need to talk about a little bit more. Okay, so that's it. I just wanted to thank my students, and then there are a bunch of references, but so that's it. So again, hopefully what we've shown here is that for the things that we're looking for in hardware root of trust, you don't really find them in the PUF designs. You don't really find them in the NVMs. And what you need is some sort of hybrid in there. And again, I think we slightly by accident, ended up. That's where we ended up in terms of the design. All right, thanks. Question.
I'm going to put you on the spot a little because
Okay.
you said this was partially a position paper.
Right.
So it seems to me, and I'm not a hardware guy at all, that you're working really hard to build a thing that maybe doesn't actually solve the problem.
Okay.
And I was wondering if you've put any thought into, how do we, rather than fix PUFs or NVMs, is there some other technique we could use that would solve the actual problem?
Okay, so I'll answer your question in a roundabout way, and you tell me if I haven't answered it after I've done. So a little while ago, I was talking to a manufacturer, a big manufacturer of embedded systems, and one of their very high up people came online in the conference call and basically said, look, you know what, PUFs are great and all, but they're not our problem. We have half a dozen ways to put a number on a chip, and that's not the problem. The problem is really getting that percolated up the design stack so our users can actually do something with it, right? And so at least for a certain segment of the vaguely secure IC design community, they're not worried about some guy spending $500,000 trying to reverse engineer the chip. They just want some high school kid in Belgium not to do it, and then everything else they just need it to be usable, right? So I think your question about is this really the problem is quite relevant. As far as the PUF community goes, I didn't have this part of the position in here. We've been working in PUFs for maybe about 5 or 6 years, and there's some work before then. Lately, if you look at the research calls and the papers and everything else, there's a big rush into the space, right? There's blood in the water, there's money, everybody, a bunch of people are moving in. And the problem with PUFs is there's a lot of stuff you can build a PUF out of on a chip. There are people who are doing resistances of metal vias, delays in flash memory, just all sorts of crazy stuff that looks pretty random. All right. Now, but if I go talk to the guys at Sandia or NSA or wherever, their big concern about PUFs is where does the randomness come from, right? That with 10,000 samples, 100,000 samples, it can look pretty random. It looks okay, right? But they don't. That's not enough, right? They really want to know. I want you to tell me from a physics standpoint where this randomness comes from, and prove to me that it's actually a good random source. And so, again, this wasn't in part of it, but I think a lot of the research people are doing in PUFs right now is kind of broken, because I don't think we need more things to make PUFs out of. I think we need to prove to ourselves that they're actually a useful widget to do, right? And I mean, one other sort of point in that direction is, if you look at the two big companies in PUFs, like Intrinsic ID and Vario out of MIT, the Intrinsic ID has been better about this, but they don't have a tremendous amount of design wins, right? If it was that good of a thing, right, you would expect one of these companies to really sort of explode and take off. But there's been a very slow adoption of PUFs in the overall space. I think, again, because it's unclear what problem they solve. And in my position here is that in some cases they don't actually solve the problem anyway. Right? Question, Virgil.
So basically, ideally, PUFs really work. They would solve an authenticity problem. So this device is authentic because its response is authentic in terms of the challenge response. It was clear from the beginning that that wasn't the case. One way they tried to correct that is to put a hash function at the end,
Right.
which, without realizing that hash functions don't necessarily produce random output. But so that's basically the problem, that you don't know where the randomness comes from, and you don't know if you have real randomness. But then there is another problem. I mean, there are many other problems. One of them is, do these authentic devices, do they do the right thing? In other words, is their circuitry in some sense producing the right function? Or do they have the equivalent of malware in them? And that's a different problem. that's at the module level as opposed to necessarily at a certain. And then the next level up is this hardware design that you have, does it have the right output behavior, input-output behavior? In other words, does it satisfy the specification? So there are multiple layers of the security problem in hardware. So basically what I think Zach was asking, are you solving the right problem? The question is, what's the right problem?
Sure.
Which one of them is the right problem? In fact, there are multiple right problems.
But again, I think that, the concern I have for PUFs is really that if you look at them carefully, they don't really do that good of a job, right? I mean, if your reliability is out here at 20% or so, this is pretty bad, right? If you take your block and wrap it with a ton of ECC, this is a problem, right? This isn't a great thing to do. Yeah, question. Sorry, it doesn't.
Oh, related to the reliability, you mentioned like 13 to 20% error rates. I'm curious, do those errors occur kind of in bursts, or are they kind of randomly distributed?
They're mainly randomly distributed, right? So what ends up happening is that you get, it's fun with these plots, right? You get, right, so in the baseline PUF, right, if you don't do anything to it, you get some sort of distribution of an electrical characteristic, and you just split it down the middle, right? You say, okay, these are zeros, that's ones, that's it, right? And then this distribution moves around, and so the individual elements, will shift essentially in random. So it's not, I mean, there's been a little bit of work recently in whether or not they're clustered or not. I don't think there's a strong correlation. It's primarily random, right? Because this electrical distribution is hopefully randomly distributed across your thing, right? So you think of like Remanence PUF, right? Each of the cells, the ones and zero distribution is pretty much evenly distributed throughout, randomly distributed throughout. So the guys that are right on the edge, again, should be distributed throughout. So you don't see, in well-designed design, any kind of physical correlation or anything like that. Yeah, Virgil, sorry.
So the reliability problems in the early designs that ages system, they also stored the hash of the expected output.
Right, they check, right.
Which, by the way, gave you a cryptographic verifiable plaintext attack.
Right.
So you could actually tell what the key was that you're trying to generate by doing the 25, which I thought was 25. And they really didn't understand crypto in those days,
But so the question is, right? If I'm just trying to store a number on a chip, right? If I do a very, very small flash memory, protected with a little bit of anti-tamper, that's pretty hard to tease out, right? Maybe some guy in a government or some very well-funded organized crime place can do it, but it's very, very hard to tease out.
So here is an idea that you may want to try. Where does the randomness come from? Actually, there is no way to prove here that there is randomness. And this guy says idea, and the other sponsors, and they say, absolutely right. But what if, and this is a fairly deterministic process, but what if you construct out of this class a randomness extractor? And in other words, you are adding to it a source of randomness from outside, and you combine whatever unique response you think the path is with this amount of randomness, then you distribute it on the output. Then you actually can prove, because there's a lot of research on randomness extractors, that in fact you are producing randomness. But you have to have a separate randomness source to extract the entropy out of whatever the number is.
Okay. Let's thank our presenter again.
All right, thanks.